Newton's laws are awesome because they allow us to predict motion. They explain why things move the way they do. And if we understand why things move the way they do, we can improve engineering design, such as in the use of cars and airbags and rockets, and we can even improve our game in athletics if we understand movement and motion as well. So in this video, we're going to state all three laws. I'll state each law separately, and then following each one, I'm going to present you with an example where you get to predict what the object or thing is going to do based on that law. So let's go ahead and get started with Newton's first. Newton's first law says that an object in motion will stay in motion and an object at rest will stay at rest unless acted upon by an outside force. Object in motion will stay in motion. An object at rest will stay at rest unless acted upon by an outside force. This law is also known as the law of inertia, because inertia is a property that anything with mass has. Pretty much says inertia is a resistance to change in motion. Inertia is a resistance, an object's resistance to change in motion. So you and I both have inertia. Everybody has inertia. Every object with mass has inertia. And the more mass you have, the more inertia you have. And this is just evidenced in the fact that, I just imagine kids, like my nieces, when they kind of grab onto my ankles, they're trying to stop me, but they can't because I have a whole lot more mass than they do. I have a whole lot more inertia. And so if I'm moving, it's really hard to stop me. I naturally, I don't like to stop changing in motion. And I'm not just saying myself, but just naturally the physical properties of who I am. I'm huge, so I take more force to stop. My body doesn't naturally want to stop. I have to apply a force to make it stop. And so we see this in car crashes all the time because when you get in an accident, your body naturally wants to keep moving in the direction you were going. And so if you get in a front-end collision, your body wants to fly right out the windshield. It doesn't want to stop. Obviously, you want to stop, but naturally, physical laws will make you keep going unless you're wearing a seatbelt or you hit an airbag. So it's kind of scary, but we can see it in these pictures here. I've actually got a side collision that I took some screenshots of, and this cart comes in from the side, and it just totally pile drives the side of this car. And you can see the crash dummies here. This is sort of a frame-by-frame thing of it, but here there's no accident in the first frame. The second frame, the accident just happened, and what's crazy about it is that the head actually moves towards the window. So you can see even here that the body wants to stay still, but the car's starting to move this direction. And then the impact has already happened. The dummy's head hits the side of the window and then bounces back, as you can see by the paint stain there. But I just think it's crazy that our bodies, we obviously don't want to choose to hit the window with our head. I would want my head to go away from the window, but the physical laws of nature and Newton's first law says that an object at rest will stay at rest unless acted upon by an outside force. And so our body stays at rest until it ends up smacking into this airbag to absorb the force and it flies off. So Newton's first, connected to car crashes. I think the easiest way to remember it is if you get in a front-end collision, your body wants to keep going, and then the car stops because it gets hit by another car. But if you didn't have a seatbelt, oh my gosh, you would just fly right out of the car. And now it's your turn. We've got some longboarders right here, and I'm going to have you predict their motion when I change this scenario. Ignore this fly for a second. We'll get to him in a second. But these longboarders are going down probably a pretty lengthy hill. They get up to 60, 70, 80 miles an hour. I mean, these guys are awesome at what they do. But I want you to tell me if this longboarder is going down the mountain and he ends up hitting a rough patch of road with his skateboard, or he hits a pothole or something like that, what will happen to the body of the skateboarder? If you said that the skateboard will stop and the body will keep going forward, you are correct, because objects in motion will stay in motion unless acted upon by an outside force. You are not connected to your skateboard, and so the skateboard will stop and you will keep going. Now, kind of a different scenario, if you take this fly and the fly hits you, is that going to change your motion at all? Is that enough force to stop you? Probably not. All right, there's not a whole lot of force in a fly. He's just going to splat on your face. So a pothole, that's enough force to stop a skateboard, but a fly, not so much. On to Newton's second law, which is actually more like an equation. Newton's second law shows the relationship between force, mass, and acceleration. So you could probably just write F equals ma. That's probably enough just to know what it is. But in a real life scenario, it's pretty simple to understand, and it makes sense because we've all lifted things before, we've all moved things, and so we understand forces, we've felt them. And so I'm going to use this picture to illustrate where the guy's hitting a golf ball. That's a very, very small mass. So you see in the equation, m is really tiny, and the force is like just a normal size. And so if you use that force on a very small mass, it's going to accelerate very quickly. And so it's just like throwing a marble versus throwing a bowling ball. Like the marble, you'll throw with a force and it will accelerate very quickly, but if you use that same force with a bowling ball, it's not going to go hardly at all. And so that's illustrated. The bowling ball is kind of illustrated with this truck. If this guy swings his golf club and he hits the truck is represented by a big M. Obviously, the A is really small. It's not going to accelerate very much at all because the force is the same, but the mass is so big, it just takes a lot more force or a lot more energy to get it to move. This is really obvious in vehicles because you have big utility vehicles that are, they only get, literally 6 or 7 miles per gallon in terms of gas mileage. And then you have these smaller cars like my Toyota Echo, which gets 30, 35 miles per gallon. And so the reason those two have different gas mileage is because one, the big cars take a whole lot more force to move because they have so much mass. And nobody likes a big car that can't accelerate, right? So we would never buy a big, massive car that couldn't accelerate. We want mass and acceleration. We want the big Hummer, but we want to be able to go from 0 to 60 in 5 seconds. And so because of that, it's going to take a lot more force, a lot more energy, and accordingly a lot more gas. Now if we get a smaller car, it kind of takes this M, the mass, down a lot smaller, but we can get, with the same amount of force, like the same size engine, we can get a lot more acceleration. But if our mass of the car is smaller, it goes really quick. And that's why in sports cars, if you look at them, they all, not sports cars, the racing cars, like NASCAR and IndyCar, the frames of those cars are just chintzy. There's this really thin kind of plastic frame on the outside, and the inside is where there's a metal, frame that kind of protects the driver. But the outside of the car is hardly anything. They try and reduce the mass in those cars as much as possible so that they can accelerate super, super quickly. And now let's do your Newton's second law example. Between this truck and this car, if I had the same engine in each car, which would never happen, but if I had the same engine in each car, the same amount of force was being applied to each of these vehicles, which one would accelerate faster? This is pretty obvious, but obviously the car, because it has less mass. And that just goes to show you that Newton's second law is pretty easy to understand. It just shows that objects with more mass require more force to get them going. And also, if you want an object to accelerate quicker, you're going to need more force. Newton's third law is different than the first two in that it deals with action and reaction forces. Stated, it says, for every action, there is an equal and opposite reaction. Newton's third law stated is for every action, there's an equal and opposite reaction. And that's true. It doesn't always seem like that, but it's always true. When you walk on the ground and you push on the ground with your feet, the ground pushes back with a normal force. It just is. All right. Newton was able to figure that out. And the same thing happens with every object in motion. So if you take a rocket, for example, the rocket pushes against the air or the water or whatever, and that pushes right back to make it go forward. Same thing with a ball hitting a baseball bat. The ball hits the baseball bat applies a force back to the ball, and pew, along with, of course, a little bit of help from the swing too, you get a little bit more force there. But anyway, even if the bat was just sitting there and the ball smacked into it, it would bounce off, and there would be another force that went against it. So for every time there's an action force, something hitting something, there's going to be another reaction force. And so your question on Newton's third is when these dolphins jump out of the water, they apply a force to the water. So my question is, what actually allows them to fly out of the water? What pushes them back? If you said the water pushes them back, you're correct. All right, the dolphins push against the water, and the water pushes them back. Just like if we were to step on the ground and go for a run, we push against the ground, and the ground pushes back. It's an action and a reaction. So as you kind of think about Newton's third law, always think action-reaction forces. That was the video for today. We went through all of Newton's laws. You should have a stated sort of definition or equation for each of the laws. And then you should also have a couple examples of each just to give you an idea of how those are played out in real life. Take care.